today I am going to discuss the applied physics in that fifth unit 5. In that fifth unit I am going to discuss nanomaterials. So what is nano? A nano is a prefix that means very small, is very small or a teeny size. Question: how small is nano? It is 1 billionth of something, is of the order is equal to 10 to the power of minus 9. So what is the scale of a nano? Is of the order of 10 to the power of minus 9. Nano length scale is nothing but 10 to the power of minus 9. So once you know about the nano scale, then I am going to discuss about the nanometer. A nanometer is 1 billionth of a meter. So nanoscale is actually a nanometer scale. So the nanometer scale range is approximately from 1 nanometer to 100 nanometer. This is the range of the nanometer. What is the accurate definition of a nanometer scale? So the actual range of a nanometer scale is 1 nanometer to 100 nanometer. So now I will talk on nanoscience. So the branch of science that deals with the study of small stuff. So what is nanoscience? The nanoscience not only explain the biological properties of a material, the nanoscience is not only explains the physics principles of a material, the nanoscience not only explains the chemistry of a material, the nanoscience is all science that works with a very small particle. So nanoscience is not a physics, chemistry, engineering or a biology. It is all of them. So now can you imagine what is the 1 nanometer dimensions of the matter? So as you all know, our human hair, if you take one human hair, the diameter of the one human hair is 100 micrometer. If you make 100 slices in one hair, apart from 100 slices of one hair, if you take one slice, it gives 1 micrometer. Again, if you take 1 micrometer, if you make it 1,000 slice, again in 1,000 slice, if you take one slice, that the diameter or a thickness or the size or a length of that particular one slice is gives the 1 nanometer. So that much a very small particle. Such scale is called as a nanometer scale. So how we are going to scale down? So from bulk to the nano, we are going to what? Reducing their dimension. We are going to crush from larger to very small or a tiny particle. So actual physical dimensions relevant to nano system. From this physical dimensions, how we are going to relate to the nano system? So as you all know about the millimeter to the micrometer to the femto. So here actually we are going to deal with 1 nanometer to 100 nanometer scale, that is the actual scale of a nanoscience. So we are going to deal with only within the scale 1 nanometer to 100 nanometer. If it is there, if it is within this scale, the properties of the material is completely dependent on size as well as shape of the material. So now I am going to discuss the introduction of nanomaterials. So the range between 1 to 100 nanometer, the matter, if you take a matter, in that matter we are going to arrange by controlling the sizes between the scale 1 to 100 nanometer, so that structure obtained that exhibits the characteristic property that is based on their size and dimensions of the material. Such type of materials are called nanomaterials. The physical state in which they exist is called mesoscopic state. What is that? Mesoscopic state. The nanoparticle is considered as a one whole dimensions are large enough to define a lattice, but small enough to exhibit properties that are significantly different from bulk. This is a bulk, this is a nanomaterial. If we compare the properties, so it is nanoparticle is considered as the one whose dimensions lies in the range of nanometer scale, are large enough to define a lattice, but small as compared to the bulk. It exhibits a better property because it having a smaller size, that is lies in the range of a nanometer scale. Now I am going to discuss the classification of a material, classification of a nanomaterial. If the nanomaterial, if you consider having a nanostructured components with at least one dimension, is between 1 to 100 nanometer. If it is such type of particles, we call it as a nanoparticles. Such materials we call it as a nanomaterials. So we are going to classify the nanomaterials based on from the dimensions. So in this case, in the bulk case, we have x coordinate, we have y coordinate, we have z coordinate. In this, if that particle is there within the box, so that particle, size of that particle is less than 100 nanometer, such particles are called nanoparticles. So that dimensions of that structure. Now, out of all the three coordinates, if we want reduce one dimension. It means we are going to suppress the z coordinate. If you suppress the z coordinate, what you will get? You will get x coordinate and y coordinate. It forms a sheet or a film. Let us take an example of a book. If you take a book, it having x coordinate, y coordinate, z coordinate. So that is bulk. So if you want to suppress the z coordinate, it means we are going removing the each pages in the book. If you go on removing the pages from the book, last page of the book is having only two dimensions. One is x coordinate, other one is y coordinate. It having only length and a breadth. Length is represented as A, breadth is represented as B, but here height, as compared to the length and breadth, height is very, very small, of the order of 10 to the power of minus 9 is height that is suppressed along a z coordinate. Such type of materials we call it as a quantum well or thin film. Thin films. So we are going to apply these techniques to make a surface coating, to form a computer chips. So the computer chips and surface coating, these are all two-dimensional objects. This is a 3D, this is two-dimensional object. What actually we are going to do? We are going to do reducing the dimensions here. We are going to reducing the dimensions. So again, if you are going to reduce z coordinate and y coordinate, if you suppress two coordinates, what will get? We will get only, if you suppress y coordinate also, we will get only z, we get only x coordinate. Here we are going to confine, we are going to will get a one-dimensional structure. Such type of a material we call it as nanowires or nano tubes or fiber kind of a structure. So that is a one-dimensional object. So if you remove all the three dimensions, it means we are going to reduce z coordinate, we are going to suppress y coordinate, we are going to suppress s coordinate. We will get a point that we call it as a zero-dimensional structure. Such type of structures in the material we call it as a quantum dot. Such type of particles we call it the nanoparticles. Examples are precipitates, colloids. Such small particle point or a dot we call it the quantum dots. It is very, very small. This is a tiny particles of a semiconductor material and it is a nanocrystalline material. This is the classification of materials. 3D is in a bulk, 2D film is in the 2D structure, nanowire is in the one-dimensional structure, quantum dot it is in the zero-dimensional structure. So now I am going to show you the how. Once you know the nanoparticle, that is a quantum dot, the dimensions of this quantum dot is very, very small, is of the order of 1 to 100 nanometer. If it is the size of that dimensions of that particle is less than 100 nanometer, now we are going to apply, why called the quantum dot? Because as you all already studied, the difference between the Newtonian mechanics and quantum mechanics. What actually Newtonian mechanics deals? The Newtonian mechanics deals with the macroscopic objects. It means the objects we can easily to see through our eyes. Such objects we can easily to apply the Newtonian mechanics, that also called the classical mechanics. But we are going to discussing here nanoparticles. It's the size of that particle is very, very small, is of the order of 10 to the power minus 9. That particles we can't see through our naked eye. So we have to apply quantum mechanics. So as the quantum mechanics we are going to apply to the subatomic particles. Already you know the subatomic particles are electron, proton, neutron. So if it is a subatomic particle, if you apply quantum mechanics to the particles, then it having both nature. What are those two? Particle nature as well as wave nature. Already we have studied dualism, and also we have studied in the quantum mechanics particle in a box of an infinite height, potential well of an width L. In this case, with the help of this, we are calculated the energy eigenvalue. So what is that expression? En is equal to n square h square divided by 8m. What is the width of the well? Here L square. In this expression, what is n? N is what? N is a quantum number. What is H? Planck's constant. What is M? Mass of the nanoparticle. What is L? Width of the box. What is N? En is the energy level. So if you go on substituting the n is equal to 1, 2, 3 and so on, this represents the quantum numbers corresponding to the energy levels. If you substitute n is equal to 1, it gives the E1, that is the minimum energy state, that is the ground state. So in the ground state, what is the probability? So if it is a particle within the box, that information is explained the wave function. The wave function inside the box is not equal to 0. Why? Already we know that the particle is there within the box. Then that gives, with the help of this, we can easily we can find the probability of finding the particle within the limit. Within the limit. Now I am going to discuss with the next point, that is a quantum confinement effect. What is confinement effect? Why are you going to apply quantum? Because you know the dimensions or the size of the particle is very, very small. If it is very, very small, then we have to apply quantum mechanics. In that, we are going to confine, what actually we are going to confine in the material? The material having a atoms, the atoms having a subatomic particles. So that subatomic particle, let us assume as an electron. We are going to confine the electron during the study of a transport properties. So how we are going to confine? So already you know, it is a, if you take a box or a cube, what is? This is a cube. In this cube, it is a, we call it as a bulk material. If you take a bulk material, in the bulk material, the particle is within the box, within the cube, within the cube. So this is the x-axis, this is y-axis, this is z-axis. Here the particle is present within the box. The particle is not on the wall. The particle is not outside the box. The particle is present within the box. It can easily, it can freely move space around the box. Such type of materials are called bulk materials. Here the degrees of freedoms are 3D. Such type of materials, it is a three-dimensional object. If you reduce one direction in the bulk material, it gives the resultant structure is a 2D structure. If you reduce the z direction, if you reduce the z direction, it forms the resultant structure, that is two-dimensional structure. That two-dimensional structure we call it as quantum well or thin film. In this case, we are going to confine the electron. The electron can move along only two directions. Either it can move along x or it can move along y direction. But the electron cannot move along z direction because we are suppressed the z coordinate. The thickness of the z coordinate is very, very small as compared to that of the x and y coordinate. So that dimensions of the z coordinate is of the order of nanometer. We are confined here, the electron, we are confined along only two coordinates. Next, again if you are going to reduce in the bulk material, again we are going to reducing z as well as y coordinate. It gives only x coordinate. We are extended the only one coordinate and remaining two coordinates we are confined. We are confined the other two dimensions. We are confined the other two dimensions here. It means the electron can move along only one direction, that is along the extended direction, that is x direction. The electron we are confined along z direction as well as y direction. Such type of material, such type of structure, we call it as quantum wire or a tube or a fiber. Now again we are going to reduce z, y and X, it gives only a small dot that is called as a quantum dot. In the case of quantum dot, all the three directions are, we are going to confine this is the quantum confinement effect. It's one of the important fundamental effects for the study of based on the structure or dimensions of the object. Here, in the first case, you can assume as a book, as a bulk material. If you go on removing the pages, if you take a one sheet of that, one sheet from the book, that is one page, as considered as the film, in that the length is there, breadth is there, but the thickness or height of that page is there, but is very, very small, is a negligible quantity as compared to the length and breadth. So that height of the paper, you can assume as the dimensions is of the order of 1 nanometer. We are going to confine the particle here. The particle we are considered here as electron. Again, if you are going to reduce the Y as well as Z, it gives a quantum wire. In the quantum wire, we are going to confine two directions. It means the Y coordinate is also in the nanoscale, Z coordinate is also in the nanoscale, but we are extended the only X coordinate. It means the electron can easily move along X coordinate. But in the case of quantum dot, we are already removed all the three coordinates. It means the electron is present in the small, very, very small position, very, very small space. Now I am going to discuss, is very important. Already we have studied in the earlier Bohr's theory. From that we have a ground state and excitation levels. Here, if you take one atom, every atom has its own atomic number. Based on that, if you read the electron configuration, from that you can easily to know how many free electrons are present in the outermost orbit. From that free electron, the transition is taking place between the valence band to the conduction band. It excites from ground state to the excitation level, and it de-excites from excitation level to the ground state. During that time, it emits the energy, that emitted energy either in the form of heat energy or in the form of light energy. It is one of the important characteristic property of a material we are using, especially in the case of semiconducting materials. So what do you call this gap between valence band and a conduction band? That is called the band gap. If you take a one single atom, this is this much of band gap. Let us take 2 electron volt. If you take 2 atoms, what happens actually here? In the valence band, we will get 2 energy levels, and even in the conduction band, we have 2 states. If you take 1 atom, we have 1 level in the valence band and in the conduction band. But if you take 2 atoms, this 1 level is split into 2 levels, 2 energy states. The availability of a state in the valence band also 2 and also in the conduction band is 2. If you go on considering the large number of atoms in the matter, see what happens as the number of atoms bringing closer and closer, the band gap goes on reducing. Again if you go on bringing, it forms the matter. So that matter in this, in the initially, that's why we are applying Bohr's atomic theory that we are studied in the atomic physics. If it is a solid, so if you want to study the solid material property, that actually we are going to study in the solid state physics, that is in the bulk material. If it is a bulk material, band gap is small, but the property, the structural property, electrical property, magnetic property and optical properties are entirely different from bulk material to the nanomaterials. So how we are going to change? Especially from, already we have studied in the quantum confinement effect, we are going to reduce their dimensions from bulk material to the nano particles, that is a quantum dot. In this we are going to reduction of particles. So in this case, especially in the nanoscience, as reducing the from bulk to the nanoscale, the band gap is increases. It is one of the important parameter helps to decide the material for a particular application, especially in the solar cells or in the LED, many photovoltaic cells, many applications based on this energy gap. Now I am going to discuss the density of states. The density of states is the one of the fundamental property of the material in the transport property of the material. What is density of states? The density of states is the number of states per unit energy range. That is nothing but the number of states per unit volume available to the electron to occupy in that particular region. Here already we have studied the energy eigenvalue in the quantum mechanics. In this, En is equal to n square h square divided by 8m L square. What is L? L is the length, n is the quantum number, is the energy. Now is the energy states. So, and from EK diagram we can easily to know what is the minimum amount of energy present in the system is of the order of 10 to the power of minus 3 meter. If you take a box of all the sides 1 mm, then what is the minimum length is 10 to the power of minus 3 meter, and what is the maximum K value is of the order of 10 to the power of minus 9 meter. Why? Because the particle size is a nanoparticle. So then if the difference between the maxima and minima is of the order of 10 to the power of 6, it means if you take the EK diagram, the availability of maxima to minima 10 to the power of 6 states are available within the small space. If you take a box that is a bulk material along x coordinate, y coordinate, z coordinate. If you take a parabolic nature, so this is the length of the box along x coordinate, that is Lx, this is Ly, this is Lz along y and z respectively. So if you take just back side of that, this is a E1, this is a E2, let us assume. So this dashed line represents the small energy difference, that is E2 minus E1, that is the energy range. That is what? Per unit energy range. Within this small energy range, how many states are there? That is what? dE. What is density of states? The density of states is the number of states per unit energy range. That is nothing but the number of states per unit volume available to the electron to occupy. Now we are going to apply, we are going to study the density of states in particular quantum structures. In the case of quantum dot, here we are removed all the 3 coordinates, all the 3 directions, all the 3 dimensions. In this case, if the density of states is calculated with the help of the energy expression, the number of states per unit energy is gives the Dirac delta function energy level minus energy state for that a particular level I. The delta represents the Dirac delta function, EI represents the energy state for a particular I state. So in the case of quantum dot, in the case of quantum dot, it is a very small, in that very small particle, how the density of states varies with the energy. Density of states varies with the energy. If you take a quantum number n is equal to 1, if you take a quantum number n is equal to 1, that is represented as E1, that is in the ground state. So it gives the density of states is increased. In between 0 to 1, there is no available states. At minimum quantum number, it having a definite levels, available states are present in the quantum dot. As you increase the next quantum number n is equal to 2, that is the first excitation level. Between first quantum number to the second quantum number, there is no availability of states. At quantum number n is equal to, in the E2 level, the energy, the density of states is increases as compared to the quantum number n is equal to 1, that is the minimum quantum number n is equal to 1. Next, as quantum numbers goes on increases to the higher energy states, that is E3. So at E3, as compared to the density of states from E1, E2 and E3, the density of states increases. In between the quantum numbers, there is no availability of states. The states are present only at particular quantum number, that is n is equal to 1, 2 and 3, that equal to the ground state, first excitation level and second excitation level. So as the quantum numbers are increases, the height of that is increases. It indicates the availability of states are increases. In the case of one dimensional, it means already we are confined the particle in two directions. The electron can easily to move along only one direction, that is along x direction. So if you compare, the density of states for 1D is it is similar to that of a 0D, only the difference is here. Only the difference is the Dirac delta function. The Dirac delta function is varies raised to minus half. It means in between the quantum numbers, in between the energy states, in the case of 0D, there is no variation, but in the case of 1D, here what happens? The density of states increases at E1. The density of states in the case of quantum wire decreases up to E2 level. At E2 level is almost 0. Again, at E2, the density of states again increases. It reaches to the almost similar to that of height in the case of a 0D, but again between 0 to second level to the third level decreases, again it increases. So this is the behavior of the density of states in the case of a one-dimensional material, that is in the case of quantum wire. It decreases because here it is a minus, that's why it is decreasing. How it is decreasing? It is gradually decreases. In the case density of states, in the case of two-dimensional structure, that is a quantum well or a thin film. In the case of quantum well or a quantum film, here the electron can freely move along two directions. It can move along two directions. If you plot the graph of density of states with the variation of energy, it increases at E1. Once it reaches the maximum levels present at the ground state, after that it is almost constant. It will not decreases. It is almost constant. Once it reaches the second higher energy level, it will not fall to minimum energy. Again it will increases. Again it reaches the maximum available state at E2 level. Again it constant. Again it reaches the next higher level. Next increases. Again constant. So what you call this? These are all called sub bands. This is first band, second band, third band. Here it is a continuity. So this is the width of the sub band. How it looks? It looks like a staircase, especially in the case of a quantum well or in the case of thin film. So in the case of three-dimensional, you know the structure of material. In the case of bulk, that is 3D structure, its density of states is proportional to e raised to half. E raised to half. Because you know the expression En is equal to n square h square divided by 8m L square. If you take n, it becomes root of e. So that's why e raised to half. How the density of states variation taking place in the case of bulk material, it is directly proportional to the energy of the particle, but it's not increases linearly, it increases parabolically. It increases parabolic nature. So see here, now I am going to compare all the four materials, bulk material to the quantum well, that also called the thin film. Next quantum wire, some are tubes also, and 0D, that you call the quantum dot or a nanoparticle. So this is the behavior of the density of state with the variation of energy of the particle. In the case of bulk material, as the energy of the particle, as the energy increases, the density of states shows the parabolic nature. As in the case of quantum well, as the energy increases, density of states is not increases continuously. It looks like a staircase. It forms a subband. This is the width of the subband. As the particle size increases, the subband decreases up to a particular limit. After that, again it forms the bulk material. It is a parabolic nature. So in the case of one-dimensional quantum wire, at E1 level, here the maximum, see here, increases. In between the quantum numbers, the density of states in the case of quantum wire decreases. Once it reaches the second quantum number, that is the next higher energy level, that is the first excitation level, again the density of states increases. The density of states, it means the number of available states. The number of available states at E2 level is reached, then obviously after that again it is decreases, it reaches to the next higher energy level, that is the second excitation level, again increases the density of states, then decrease. This process is continuous. This is the behavior of the variation of density of states with the energy in the case of quantum wire and in the case of quantum dots. In the case of quantum dots, how the density of states variation with the energy, it looks like a discrete nature. It looks like a discrete nature, that also called as quantization, that also called as quantized. It means at n is equal to 1, E1 it having a number of available states, at n is equal to 2 it having some number of available energy states, but in between E1 and E2 there is no availability of states. So the energy levels in the case of zero dimension, that is in the case of quantum dot, it is a discrete nature. Now I will discuss the synthesis of nanomaterials in the next class.